So hi everyone and welcome to the Applied Topology Network online seminar. The speaker today is Nina Otter and she's going to tell us about the magnitude of a metric space.
Okay. Hello everybody and good morning, afternoon or evening, wherever you are. So first of all, I would like to thank the organizers for inviting me to give this talk. Today I will talk about the magnitude of a metric space, which is an invariant of metric spaces that was introduced by Tom Leinster around 2010. And it arose from his study of the generalization of cardinality-like invariants. And so more or less what I will do during this talk is I will first introduce the magnitude for finite metric spaces and talk about some of the properties of the magnitude. And then I will talk about two different current research areas. One is the convex magnitude conjecture, which involves the magnitude of compact metric spaces. And the other one is the, let's say, the area around magnitude homology, which seeks to find a categorification of magnitude in a similar way as, for example, singular homology categorifies the Euler characteristic. And then I will explain how magnitude homology is related to persistent homology, and also somehow how maybe these two different points, 2 and 3, could be related. So yes, so first the magnitude. So as I said, Leinster came to define the magnitude for a finite metric space being motivated by the generalization of cardinality-like invariants. So the definition I will give here is very hands-on, and because it's, let's say, it's the simplest definition I can give in this talk, but yes, the motivation really comes from studying the Euler characteristic of a finite category and so on. And so for a finite metric space, one can define this matrix Zx to be the matrix with entry in the ith row and jth column to be the exponential, so e to the minus, and then the distance between the 2 points. And when this matrix is invertible, one can define the magnitude to be the sum of the entries of the inverse matrix. One can define it more generally also when the matrix is not invertible, but it has a very simple form in case it is invertible. And then, right, in general, one is not interested in studying a metric space per se, but only up to, let's say, rescaling, for example, of the distances between the points. So what can one can consider giving a metric space the family of metric spaces that one obtains by rescaling the distances by a positive real value t, and then one can also define the metric space rescaled by 0 to be the one-point space. And so one then introduces the magnitude function, which captures how the magnitude varies as we rescale this metric space. And it is a partially defined function because, because the magnitude might not be defined for all values of t. And so the simplest example is, of course, well, the one-point space, and for that we have that the magnitude is 0. The next simplest example is the two-point space. And in this case, we have that as t increases, the magnitude function approaches 2, which is the number of points of the space. So already here we see that we could interpret this magnitude as giving us the effective number of points of the space, right? So the more we increase c, the further the points are apart, and so we can think of this as telling us that this space looks more and more like a two-point space. And in fact, right, as I said, this magnitude was introduced by Leinster in 2010, but in fact it had already appeared in the 90s in a biology paper, in a paper on the study of diversity of species, and it also there it actually captured, it was the intuition for this quantity was that it would capture the effective number of species. So that's also a very interesting connection. And so this interpretation of the magnitude as giving us the effective number of points of a space is also somehow further strengthened by these properties that are satisfied by arbitrary finite metric spaces. So we have that, okay, it might not be defined at all points, but at least it's not defined only for a finite number of points. And in the limit as t goes to infinity, we have that it gives us the cardinality, so the number of points. And it is also an increasing function in t, for t sufficiently large. And so these are also all reasonable properties we would expect, right? Cardinality like invariant to satisfy. And somehow the fact that I'm listing these properties here also highlights that the magnitude function can be really badly behaved. And so in particular, the smallest metric space for it exhibits many different types of bad behavior is the metric space which is associated to the complete bipartite graph on 3 and 2 vertices. So here we have 3, so in total 5 vertices, and then we have all possible edges between a subset of 3 vertices and 2 vertices. And we make this into a metric space by taking shortest paths. And so here we have that there is this value of t, logarithm of square root of 2, for which the magnitude function is not defined. And then we see it actually can be decreasing, can take on negative values. And it can also, yes, take on values that are actually larger than the cardinality of the space. But there is a very nice class of spaces for which the magnitude satisfies many properties that we would expect cardinality-like invariant to satisfy. And these are called positive definite metric spaces, and are those for which this matrix is positive definite. And for such spaces, one can show that the magnitude function is, yes, well defined, so it's defined at all points. It is non-negative, in particular it is greater or equal to 1, and also the magnitude of a subspace is smaller than the magnitude of the whole space. And yes, and examples of such spaces are finite subsets of LP spaces, real and complex, so finite subsets of real and complex hyperbolic spaces, ultrametric spaces, and so on. And there is this very nice overview by Lenser and Meckes from 2017, and there they give an overview of most of their results in the research on magnitude up to 2016-17 when they wrote the paper. And so many of the things I said here I actually took from that paper, and of course they give a, let's say, survey of results proved in other papers. But so this would also be, I would say, this paper would be a good paper to start with if you would like to learn more about magnitude. And yes, and so now, of course, we have until now talked about the magnitude of finite metric spaces, but it makes sense to try to generalize this for more, yes, arbitrary metric spaces. And the first place to look at is usually as compact metric spaces. So there are several different ways in which magnitude has been defined for compact metric spaces, and one which has also been shown to be somehow the correct way to do this is an approximation by is when we look at the magnitude of finite subspaces of a compact metric space. So if
Nina,
yes,
I'm sorry to interrupt. So we have one question, referring to the previous slide. Does this mean that finite subsets of Rn with Euclidean metric are positive definite?
What is the question? Sorry, I didn't. Did you ask a question?
So finite subsets of Rn with Euclidean metric.
Are they positive definite?
Yes.
Yeah, so that's the question. Sorry for the interruption.
Okay, sorry. Yes, I didn't.
Yeah.
Sorry, yes. Yeah. So in particular, yes, finite subsets of Euclidean space in particular are positive definite. Yes. If that was there. Sorry, I thought it was yes. Okay. Okay, so if you consider compact metric spaces with the property that all finite subspaces have magnitude. So if you remember, this means that this is positive definite, means that the matrix is positive definite, and in particular we have the result that the magnitude is well defined. Then one can define this, the magnitude of the compact metric space to be the supremum of the values of the magnitudes for the finite spaces. And of course, for this definition to make sense, one needs to have some, let's say, continuity result with respect to this, let's say, value of the supremum. And yes, and in fact, this it was shown that this supremum, this is, I think, lower semi-continuous as a function of X, where one considers the family of all compact metric spaces satisfying this property, and together with the Gromov-Hausdorff distance. And again, here there is, let's say, this was not proven directly in this paper, but in this paper they, let's say, give I think, a very nice, they introduced this in a very nice and natural way. Yes, let's say the different, they compare also different definitions of magnitude for compact metric spaces. So again, I would suggest to first look at this reference. And examples is, well, if you look at the closed interval of length L, then its magnitude is given by half of the length plus 1. Or if you look at the circle of circumference L, then its magnitude is given by half of the circumference plus a function of L that goes to infinity as L goes to 0 as L goes to infinity. And in 2013,
can I interrupt
yes?
with a question? Sorry, if you go back a slide, I lost the dependence on t. So for that interval and that circle example, is that for a specific choice of t? Maybe you're fixing t to be 1?
At the moment, I think you're fixing t, yes. Yes, and
okay.
Then, yes, yes.
I mean, L and t is same thing, sort of. Yeah. I mean, one, you
yeah,
could
exactly.
It
depends on, exactly, yes. Yes.
I see.
But at the moment, yes, you're fixing, yes. Yes.
Thanks.
And so in 2013, Leinster and Willerton, based on several, let's say, computation, heuristic results, and let's say plausibility arguments, they suggested this conjecture. So they suggested that for compact and convex subsets of Euclidean space, one has that the magnitude is this sum, is this, let's say, yes, this polynomial expression in T, where the coefficients are given by the intrinsic volumes divided by the volume of the unit ball. And so yes, for those of you who don't know about intrinsic volumes, these are the nth intrinsic volume is just the ordinary volume. The zeroth intrinsic volume is the Euler characteristic, and one has the n-1 intrinsic volume is, I think, something like 1/2 of the surface area and so on. And then there are all sorts of values in between, let's say in between 0 and n-1, and not much is known about these intrinsic volumes, but they're also very interesting, let's say, objects of study. And so in that sense, if this conjecture were true, and we will see in the next slide, it's actually not, but this would be very, let's say, could be very helpful, because then one could, one could use, let's say, the magnitude to understand more about the intrinsic volumes. And so, yes, this was this convex magnitude conjecture was disproved in 2015 by Barcelo and Carberry, because they showed that for the 5-dimensional unit ball, we have that this is not a polynomial expression, but it's actually a rational function in the radius of the ball. Based on this, Kimperlein and Goffing suggested in 2017 an asymptotic variant of this conjecture. So they suggested that the magnitude function has a meromorphic continuation, where here we have, this is in the limit as the real part of t goes to infinity, and this coefficient Cj is proportional to the intrinsic volume, at least for these values. And so still we would have some, let's say, relationship between the magnitude and these intrinsic volumes. And as far as I know, this is the state of the art for this conjecture. But yes, there is a lot of research related to magnitude in, let's say, geometric measure theory and so on, because it has been shown to be captures many invariants that people study, like dimension, volume, and so on. And so it generalizes many of these invariants. And so in that sense, this is one of the reasons there is so much interest at the moment in magnitude. And so now we will jump on in a completely different, in some sense, current research area, which is the one that explores the categorification of magnitude. And so if you go back to our favorites, at least I think in this seminar, cardinality-like invariant, that is the Euler characteristic of a topological space, right? And we know that the Euler characteristic is can be written as the alternating sum of the Betti numbers, right, whenever this sum exists. Right? So, and what one says is that singular homology categorifies the Euler characteristic. And so a natural question to ask is, since, as I said, the magnitude is actually cardinality-like invariant, is there a homology theory for metric spaces that is related to the magnitude in an analogous way as singular homology is related to the Euler characteristic? And in 2015, Happort and Wilderton answered this question in the affirmative for finite metric graphs. So these are finite metric spaces as obtained from weighted graphs, where one computes distances as shortest paths. And in 2017, Lancer and Schulman generalized this to arbitrary finite metric spaces. And what they did is, they introduced a very general theory, a homology theory for enriched categories. But I will now not go too much into the details here and just explain for the special case, let's say, of finite metric spaces, what this boils down to. So they introduced the magnitude homology chain complex, which is a chain complex which in degree n is given by a graded abelian group, graded by positive reals, and the homogeneous piece of degree L is given by the free abelian group on ordered tuples of points in the metric space, so that the sum of the pairwise distances is exactly L. And then they define the boundary map as follows. This is given by the alternating sums of maps of this form. So we have that is non-zero, and then the triangle inequality is a strict equality. So if we drop the ith entry here, we have that the sum of the pairwise distances does not change. So it is still L, and it is zero otherwise. And this is for, when I is in between 1 and n minus 1, and then and also for I, when I is 0, we define it in a similar way, and then similarly, when I is n. And then they have this result. So they have that if X is a finite quasi-pseudometric space, so the fact that we have this, let's say, more general yes, more general metric spaces is because, as I said, they actually study homology theories for enriched categories, and so one can see a metric space as a special type of enriched category, a Weyl metric space, and at this level of generality, it is actually, yes, a quasi-pseudo metric space. And they show that for such metric spaces, we have that that this homology theory categorifies the magnitude. So here on the left-hand side, we have the magnitude of the metric space. And on the right-hand side, we have, yes, we have this alternating sum. And of course, a remark to, because I have given at least versions of these talks already, and then a question people have is, but don't we have a real number on the left-hand side? And how can we express this as this alternating sum on the right-hand side? Well, what you should keep in mind here is that this is, yes, it's a graded, an abelian group graded by, no negative reals. And so actually here what one does is one can define, so yes, sorry, I'm not, yes, what I want to say is I'm not actually giving many details, but one can define the Euler characteristic very generally for any dualizable object in a symmetric closed monoidal category. Don't remember if, yes, I guess you need close. And so in that case, it is then an element of an endomorphism ring of the unit and so on. And yes, it would then be here, actually, yes, it would have a real number. But it's not apparent, at least, just staring at this like this, it's not, wouldn't be clear why you actually have a real number. And so this homology theory, it categorizes magnitude for finite metric spaces, but it fails in general. So there are these two papers from 2018 in which they appeared, I think, yes, in the same month. And in both papers, it was shown that for convex subsets of Euclidean space, magnitude is trivial in degrees greater than 0. But it is actually a magnitude homology. But it is actually known, the magnitude is actually known to capture many important invariants of convex subsets of Euclidean space, and so it can't be. So in that sense, this shows that while this might be a step in the right direction, it is still not a complete answer to this story, to finding a homology theory that categorifies the magnitude. And as I said before, also, it captures when the triangle inequality is a strict equality. And so at the end of the paper, Lenzer and Schumann list a series of open questions, and two of these are, yes, whether there is what they call a blurred version of magnitude homology that also that does not only capture when the triangle inequality is strict. And the other one is that somehow one always has the feeling when one sees first magnitude, for example, this plot of the magnitude function for the metric space of 2 points, that somehow it should somehow be related to persistent homology in a way or another. And they ask if there is some relationship. And so I will, in the next couple of slides, at least give my own answer to this question. Is yes, I will introduce a blurred version, and I will show that this blurred version is actually the persistent homology of a specific filtered simplicial set. And this filtered simplicial set is the simplicial set that at level epsilon is given, has set of n simplicities given by the order tuples of the metric space, where we have that the pairwise distances are the sum of the pairwise distances is smaller or equal to epsilon. And one can then define the blurred magnitude homology of a metric space to be this construction. And so what this is here is, so we have this, right? So we have this filtered simplicial set, and then we are taking chains of unnormalized simplicial chains. And we are tensoring this with a functor of coefficients that is supported at intervals. And so this symbol here is, yes, this would be a cohend and so on. And the details here do not matter. You just have to think of this as being just, we have, as for example, as we usually do, right, in persistent homology, we have some filtered simplicial complex, and then we just associate to this right, a chain complex of simplicial chains. So here on the left-hand side, we are doing the same, and only here we have this, let's say, twist, that we are transferring this with some functor of coefficient. And yes, and then one can consider this whole package as just giving us a functor from this poset category to the category of chain complexes of abelian groups. And something I have not said here is that somehow, as I said, there is actually in that sense really a twist, because to have this cohend construction, one needs these two functors. So this functor here, C and X, and the functor that is related to the functor of coefficients to have opposite variants. And one has that then actually this, the name blurred magnitude homology is justified because this blurred magnitude homology really captures when the triangle inequality is not strict. And one can also show that it is actually the persistent homology of this enriched nerve. So one could actually take this to be the definition. And of blurred magnitude homology. And then one can then also try to relate this to, let's say, other types of filtered simplicial sets that we, for example, yes, consider in topological data analysis, the Vietri strips. Well, in this case, yes, I'm not talking about simplicial complexes, but yes, they're just a simplicial set version of the simplicial complex. So we would have here that this is the filtered simplicial set, which at level epsilon has the set of n simplices given by order tuples, so that yes, the pairwise distance is a smaller or equal than epsilon. And then the Vietri homology, this was the homology theory introduced by Vietri, or at least an equivalent formulation of the homology theory introduced by Vietri. And this is also in his paper from the 1920s. This is also where the Vietri-Rips complex was actually first introduced, is the categorical limit as epsilon goes to 0 of the homology of this of the chain complexes associated to this simplicial set. And one can then relate this to the blurred magnitude homology. So we have that in the limit, as epsilon goes to 0, the blurred magnitude homology is Vietri homology. And on the other hand, we have here, this is, so the difference between this expression and this expression is that here we have, so whereas here we have functors that are supported at intervals, here we have functors that are supported at points, and one can show that this is an equivalent, this is a characterization of the ordinary magnitude homology. And so here we have that in the limit, ordinary magnitude homology is trivial. And right, as I said already before, it has been shown that actually magnitude homology for convex subsets of Euclidean space is trivial in degrees different from 0. And somehow this is another way to see that it's somehow badly behaved homology theory. And so yes, as I said, in the limit, blurred magnitude homology is Vietri homology, and Vietri homology for example, compact metric spaces is actually homology, whereas ordinary magnitude homology is trivial. And so, and actually, as I see, I'm actually quite early, but yes, there will be enough time for questions. So, so in that sense, yes, blurred magnitude homology seems to be at least a step in the right direction for the definition of magnitude homology, because of this, for example, relationship with Vietri's homology. And another observation is that it might give insight also in the convex magnitude conjecture. because if you maybe go back, or at least yes, at least also the other version, but so that zeroed intrinsic volume, as I said, is actually the Euler characteristic. So in that sense, we would want, when all the other terms drop, for when t goes to 0, we would want to recover the Euler characteristic, right? So in that sense, in this limit behavior of magnitude homology that we have seen at the end, we see that magnitude, blurred magnitude homology gives us back the ordinary homology. And so in that sense, this is also another, let's say, this also seems to also suggest that this is somehow at least the right direction in which to go. And yes, it could give further insight into this convex magnitude conjecture. And yes, so this would be the end of my talk. There are, of course, many technical details I also took out from other slides that I had from other talks. So I could have, yes, I can try to grab some slides from other talks if somebody would like to see more details about, for example, this last part, how one constructs the blurred magnitude homology and so on. Yes.
Okay, great. Any questions?
I have one question. Hey, can you give me some, Nina, some intuition about what it means to blur magnitude homology? I think I got lost in the algebra.
I'm sorry, what was the last thing you said? You were lost? No.
Some intuition as to what it means to blur magnitude homology?
It's in that sense, it's really, I think it's this construction with so what happens with ordinary magnitude homologies, if one looks at this, let's say, equivalent formulation, taking this coend with this functor of coefficient supported at points, is that one really sees that ordinary magnitude homology forgets this information that is so vital for persistent homology, this information that is given by these inclusion maps, right? We have, for example, in a filtered simplicial complex, right? Or in this case, simplicial set. So ordinary magnitude homology forgets that information, whereas in the blurred version, we are actually keeping track of that information, right?
Oh, I see. Yes. Okay.
So in that sense, that is, yes, if we are approximating, right, the space in this way, that would be vital information that we want to keep track of, right, as we do in persistent homology. So it is not, you could see ordinary magnitude homology in some way as not being, yes, let's say functorial, right, in that sense, right? It's not keeping track of informations given by maps, these maps in between the different, let's say, simplicial sets in the filtered, simplicial set. Or at least functorial in a degenerate way.
I had a question, Nina.
Mm-hmm.
So, I mean, magnitude is defined not only for metric spaces, but for many other types of mathematical objects, I think. I mean, that's maybe where the definition came from. Do you think there's interactions with persistence there in those other settings?
In those other settings, so you mean at a more general level?
Sort of just like the perspective, you have interleavings, you know, and other types of categories or...
Interleavings, what do you say?
Yeah. You know.
Well, I mean, yes, I mean, in that sense, magnitude is just, I mean, the reason it's called magnitude is, I think at some point also to not call everything an Euler characteristic. I think there is one paper in which Lancer writes that at some point, he was calling it, I think, Euler characteristic, but then at some point, just if everything is Euler, then it's a bit confusing, right? So I think that was the reason also he called it. And then, of course, magnitude, I mean, the name itself gives some intuition, right? But yes, as I said, I mean, one can define Euler characteristics right, in a very general setting. Yes, so one could also, for example, ask, for example, right, even just let's say here, let's forget about magnitude in that sense, and let's just look at persistent homology. is there an Euler characteristic for persistent homology? That would be a very interesting question for, yes, topological data analysis, right? So can we go back that was be interesting, right? Because somehow we are motivating by categorifying something, we find something else, and then we want to decategorify and go back, and that could be give maybe it would give maybe it's okay, maybe it doesn't exist, right? But what is reasonable to expect is it doesn't exist. It exists at least under some finiteness conditions. And for example, it could be that we need to no longer work with simple sets, but actually go back to working with simple complexes. And then if it exists, then is it the magnitude or is it something else? And what kind of information about the metric space does it give us? And of course, and then also the interesting question is, well, what different type of information does it give us if you consider different types of filtered simple shared complexes or sets, right? Because here we have Vietoris. Yes, for example, also already for the Vietoris rips compared to the enriched nerve, and then we have other types of filtered spaces that we could consider, right? So yes, in that sense, that could be very interesting, yes, direction to take and study, yes. Since, yes, already the magnitude encodes so many invariants, right? And could be that we can encode, yes, maybe the same or maybe not, but it could be that we can encode different types of, let's say, invariants that are already studied, right?
Thank you.
Okay. And so Nina, you said that this was introduced, like that the magnitude was introduced by biologists. Do you know anything more about like their applications and how they got to it?
It was actually, yes, in the 90s. So yes, they didn't call it magnitude, but it was, I mean, I can point you to the reference that Lancer gives. I can't, okay. They were really trying to study the diversities of species, and I think, yes, it's somehow to optimize some, let's say, problem there. And no, I can point you to the reference, yes. But there is also actually in the paper, the one by Lancer and yes, they also give references to some other work that has been done in trying to relate now this magnitude to this study of biodiversities of species. Okay. So I can, it is actually, yes, in the paper I can say, yes, I don't know. Yes, it's just in this paper, the one I gave the reference to at the beginning.
Okay, perfect. Okay, great. Yeah, thank you.
Where is it? Here. Yes, exactly, in this paper. They list also, as I said, this is really good because it's a review paper, right? So and also they give several references, I think, in the introductory section to work that has been done in relating, yes, this study in biology.
Okay, very cool. Yeah, thank you. Are there any other questions, Nina?
I had a question, kind of sort of going back to the beginning. You mentioned that the magnitude was kind of measuring the number of important points in the space. I was wondering if there's a way to, effective points in your space, I guess. I was wondering if there's a way to kind of pull out those points. You know, given a T, can you pick out the points in your metric space that are kind of corresponding to that T value?
You're saying if there is some value of T, let's say large enough, for which you can actually infer the number of points?
Mm-hmm. Yeah, so like in your example that you showed with the biologists, or the 2-point space, you know, went from 1 to 2, or maybe if it was higher, it was maybe if you had more points in your space, could you, for a given value of T, could you pick out the actual points in your space that are considered like the meaningful points?
Meaningful points, well, I guess. Okay. Well, one has in general that if you have n points in Euclidean space, then one can write, let's say, where is it? As we have written here, the magnitude would be given by n plus a function in t, where also there, right, it goes to, yes, of course, infinity as t goes to 0 as t goes to infinity. But I wouldn't know now, I don't know if something has been done in that sense to try to estimate for which t yes, I wouldn't know. Because the problem is also that, right, we have these properties, but for example, it is not true in general that this is actually smaller or equal to the cardinality of the set. So that's also why this is not written here. And there is, I think, a paper by Simon Willerton, I think, in which there are some competitions about this. Don't remember now exactly where they, but I can look up the reference later and send it if you're interested.
Sure. Yeah. Thanks. I think that answered my question.
So one analogy I've heard when I've heard people talk about magnitude earlier is that for the simplest cases, say the 2-point case, you start out at 1 because if you shrink your 2 points very much, they kind of look just like 1 point. Mm-hmm. And in the limit as they slide apart, they look like 2 points. Mm-hmm. So I find myself wondering, and I'm asking you to speculate here, whether we could generate a clustering method from the underlying ideas of magnitude, or from the theory of magnitude or magnitude homology.
A clustering is okay. So how would you? Of course, I mean, it would be very nice with a continuous hierarchical clustering, right? In some sense, is that what you're thinking of? Yes. Mm-hmm. Yes. Mm-hmm. Sure. Yeah. Yes. Of course. Yes. Makes a lot of sense. Yes. I guess so. Yes. And then you could have ways to just compare these functions. Yes, the magnitude function, right? You get. Yes, and then I mean, if it's just, let's say, if just the data sets for which you studied these are just finite sets of finite points in Euclidean space, then that should be fine, right? Of course, it depends then what you want to apply it to, right? Because as we have seen, right, it's very, very simple, actually. Small metric space has all sorts of bad behavior, right? So you would not want to use it, for example, for just any finite metric space. Right. So in particular, you could not use it just for any weighted, what's called graph, right?
Right.
So in that sense, yes, it's limited in its scope, at least. Spaces you can apply it to. But yes, if you have just points in Euclidean space, then yes, those are right positive definite spaces, and so you could do something like this. Yes. At least you could do this and then try to compare to other methods, right? And see what type of information you can get. Yes, maybe in that sense, it's also somehow the feeling I have is when one sees this, right? Especially this example, and thinks, oh yes, somehow, yes, this looks like, exactly in that sense, a continuous version of hierarchical clustering, and somehow, at least for me, that was when I felt this should be related some way to persistent homology, right? But then, at the beginning, I had tried to look at this, right? Somehow this would be related to, let's say, we can look at the barcode, right, in degree 0 and so on. But then I also realized somehow in this, if one tries to relate in this way, I think it's really two different ways. We are scaling the space here, whereas to how we are scaling the space in persistent homology, right? Because here we are really taking 2 points and we are throwing them apart, right? Whereas in persistent homology, the distance is fixed and we are growing the poles. So it's really two different ways to scale the space in that sense. Yes.
Okay, so thank you, Nina. So I would, before we all leave, I would like to ask everyone to unmute themselves so that we can clap. Yeah, very good. So Nina, thanks again. So with that, I'm going to stop the recording, but you feel free to stick around for as long as you want for an informal debate.